Great, thank you for the introduction. And first, I was hoping to be able to join in person, but Stanford's graduation is in 3 hours, and so I'll be giving this talk, going to graduation, and then flying to Vancouver tonight. But if I hope to maybe see you in Vancouver tomorrow. So today I'm going to talk a little bit about distribution shift, and I think this is a problem that's pretty relevant in autonomous driving. And I'll really be talking about the conceptual algorithms that I think are useful for autonomous driving, and we won't be seeing very many specific applications in driving, but I think that some of the ideas should be useful. So as motivation, I think we've seen a number of success stories of machine learning working really well when you have a really broad training distribution and when you're evaluating it on data that looks like the training data. But I think that there's a lot of scenarios where the test data sets or the test examples that your system is seeing is a little bit different from the things that are seen in the training data. And to handle these kinds of scenarios, I think we need new benchmarks that have imbalanced data distributions or are not independently and identically distributed, as well as new methods that use assumptions beyond kind of the standard IID assumption. So as some examples of distribution shift, we could have distribution shift over different domains or different subpopulations. So for example, in a content moderation setting, you might want to predict if comments are toxic or non-toxic. On the test distribution that is from the same, if the test set is from the same distribution as the training set, you get 92% accuracy. But if you actually look at kind of different parts of the distribution, the accuracy drops to 69.2% on non-toxic comments mentioning the Black demographic. And so this is problematic from a fairness standpoint, and it's also problematic from a distribution shift standpoint. And we like to develop machine learning systems that can actually handle this kind of distribution shift. And as another example, in molecular property prediction, if you want to predict the biological activity of a molecule, you can get 34% average precision on test molecules from training scaffolds. But then if you evaluate on held out scaffolds, the accuracy drops significantly. And these are just two examples of data sets that we curated and put into the WILDS benchmark that includes really a range of problems, including kind of computer vision problems, as well as some of these problems right here. And it was put together by Pengwei and Shiori, and they're really hoping that this is a resource for the community. So if you have any feedback, feel free to reach out to them. And then beyond kind of domain shift and subpopulation shift, we also see scenarios where shift happens over time. And as a couple examples of this, if you try to classify yearbook photos over time, you can get a training accuracy or accuracy from the training distribution that's around 98%, whereas that drops significantly as time shifts forward. And similarly, if you are trying to predict mortality, you get on the mimic data set, you can get a pretty high training accuracy, but performance drifts significantly when you move towards a shifted distribution into the future. And these are both examples from the wild time benchmark that we curated that has 6 different data sets, again, from a wide range of applications. Now, we kind of put together both of these benchmarks, and I wanted to mention a couple takeaways from that benchmark creation process that I think maybe are a little bit atypical or something that you don't normally see in a standard research process. So the first takeaway that we found is that we looked at some distribution shifts, and we actually found that there were some distribution shifts that don't necessarily cause a drop in performance. And so one of the data sets that we considered for the WILDS benchmark was the BDD 100K driving data set, and doing object recognition in that data set. And we curated the data such that the training data set and test data set had a distribution shift either in the time of day or in the location. And we actually found, at least in this data set, that the kind of out of distribution performance was generally pretty similar to the in distribution performance. We didn't really see a significant drop. And so in some ways that's good. And it means that there are some forms of distribution shift where we don't really need to worry too much about that particular form of distribution shift. And for some more details on the applications we considered in wilds, we actually have a very detailed appendix that considers a number of these different things, including this object recognition set. Now, I'll say that I don't think this means that distribution shift isn't a problem in driving whatsoever. I suspect it's actually a pretty substantial problem, but it just is that on this particular data set, it wasn't a problem for location shifts and time of day shifts. Another finding that we found was that sometimes we would observe a drop in performance, but it wasn't actually caused by distribution shift. And what I mean by this is this is a plot showing the accuracy on the yearbook data set over time. And for this particular plot, not the other plots, but for this particular plot, we were actually training on all of the years, not just the years up until 1965 or so. And we were actually considering putting the cutoff between in distribution and out of distribution right in the middle right here. And basically, this is just something that you need to account for when thinking about distribution shift, and think about how there are just going to be potentially some years that are harder than others, or some domains that are harder than others, and you want to try to account for that when actually benchmarking and evaluating your system. Cool. And then when we were curating wilds and wild time, we wanted to specifically include data sets that have drops in performance that are caused by distribution shifts, such that researchers that are interested in distribution shift can really study that problem in a fairly isolated way. Great, and then I also like to mention that some kinds of distribution shift are simply going to be impossible for a machine learning system to solve. And there needs to be some natural sources of leverage in order to actually improve performance under distribution shift. And so this could be things like domain information, unlabeled data, possibly timestamps from your data. And we wanted to actually pick data sets in both wilds and wild time that actually have this sort of possible source of leverage that might enable algorithms to do better under shift. And then the last thing that I'll mention is that in the results, we actually evaluated a number of methods for tackling distribution shift, and we found that some methods are helpful in some scenarios, but there was no kind of silver bullet that helped across the board for all data sets. And this suggests that we need methods ideally that can handle more distribution shift scenarios, but also be thinking about how we might characterize distribution shift as a problem as a whole, and understand like when we might apply one method versus another method. Great. So that's a little bit about kind of benchmarking distribution shift. Now, I'd like to talk a little bit about the other side of, say we think that there might be a distribution shift. What should we do about it? And I think this is actually a really challenging problem, and it's a problem that we've been starting to try to think about a little bit. And I think there's two things that we could think about doing. One is trying to detect when there might be a shift and help models know what they don't know if they kind of don't know the answer because the distribution has shifted, and also ideally be able to improve model predictions under some distribution shifts. So I'll first talk about this first point of, can we actually detect a shift in the distribution? So this is motivated by, I think that it's motivated by the fact that I think that there are scenarios where it's really useful to refrain from making an answer rather than actually trying to make an answer and making it correctly. If you want to, for example, defer to an expert, or if you want to kind of get more labeled data from that part of the distribution, it's really useful to know if the model is inaccurate in some regions, and ideally being able to do so without any labeled data from that target distribution. And this can in some ways fall under two existing problem settings. One is out of distribution detection, which is typically cast as the problem of determining if an input, such as an image, comes from an unseen class label, such as an object that you've never seen before, or something like that. And the second version of this problem is selective classification, where your goal is to only classify inputs that you're likely to get correct, and refrain from making predictions on things that you're not likely to get correct. And unfortunately, for these two problem settings, there isn't really a prior approach that consistently performs the best. There's some prior work that was trying to actually study different methods, and this motivated some of our work in studying this problem. Now, one framing that we came into this project with was that we felt that avoiding incorrect predictions in many cases may be more important than trying to make predictions on everything. In the sense that you kind of rather be conservative in many scenarios rather than trying to go for full coverage of your data set. And so from that standpoint, we wanted to try to encourage the model to be unconfident on new out of distribution inputs, such that it's unsure about those inputs and kind of conservative about those kinds of inputs. So really the key idea is, well, first, the key challenge here is that when you have distribution shift, it's really hard to anticipate the full range of possible ways the distribution can change. I think this may actually be extremely difficult. And so we're going to try to actually sidestep this key challenge and get some sort of representative examples of your target distribution inputs. And we'll refer to this as our uncertainty data. It doesn't have to be labeled data. It can just be unlabeled data from our target distribution that we haven't yet collected labels for. And then fine tune our model to both minimize the training error and minimize the confidence on this uncertainty data. And what this kind of fine-tuning objective looks like is something like this, where this first term is just a standard cross-entropy loss. It's kind of the negative log likelihood of the label given the input. And the second term is confidence minimization. So we're minimizing the negative. Well, so in this case, we're basically there's a couple ways to write this, but one way to write it is we're basically trying to minimize the negative log likelihood of the uniform distribution given the inputs from your unlabeled distribution. So essentially, this is kind of a cross entropy loss to the uniform distribution, which is the distribution in which you are least confident about your input. And then there's this lambda term that will kind of control the strength of this regularization. Cool. So this is our objective. Now the key question is, what is this uncertainty data? Like, where does this come from? And we studied two different scenarios. One scenario is that this corresponds to unlabeled data from your target distribution, such as if you're deploying in a new city, this would be unlabeled data that you haven't yet gotten ground truth labels for from that new city. This is often referred to as the transductive setting in machine learning. And I should note that it may also be a mix of out of distribution data and in distribution data. It may include data that kind of looks like the training data. And then another thing that we'll look at is having the uncertainty data simply be actually from an in-distribution validation set, but specifically the misclassified examples from this in-distribution validation set. Now, one other thing I should mention is that if this uncertainty data includes some in-distribution data, we're going to be minimizing confidence on that in-distribution data, which you'd think is kind of the wrong thing to do. But one of the key insights here is that this regularizer is going to have a different effect on in-distribution examples versus out-of-distribution examples. And this is because the in-distribution examples are going to have this training error term that's going to counteract the confidence minimization, whereas out-of-distribution examples are not going to have kind of the training error that's counteracting those data points. And as a result, we'll actually be minimizing confidence on our out-of-distribution examples. Great. So we refer to this as data-driven confidence minimization, or DCM. And before I get into some of the empirical results, there's actually a really nice theoretical result that you can show, which is that if your uncertainty data corresponds to your unlabeled test set, you can show that the model that minimizes the TCM objective, or sorry, the DCM objective, there's a typo there, is you'll get a model that actually lower bounds the true label probability. And so essentially you'll get a conservative model that, that outputs probabilities that are under the true label probability. And so this is pretty nice. And the assumptions for this theoretical result is really just that you need a sufficiently expressive model class. And it doesn't make any assumptions on model generalization. And then the other thing that you can show is with some additional smoothness assumptions, you can show that this method will provably detect out of distribution examples, even if your uncertainty data contains both in distribution examples and out of distribution examples. Great. So now let's also look at the empirical results. So we start with OOD detection, and we looked at a number of different metrics, but I'll focus here on the false positive rate for a given true positive rate for detecting out of distribution examples, as well as area under the ROC curve and area under the precision recall curve for binary kind of in distribution versus out of distribution classification. There's a lot of prior methods for out of distribution detection, and we compared to a number of them. There are a couple different kind of ways of categorizing these prior methods. Some of them are simply just looking at kind of the softmax probabilities or the distance between embeddings, distance in the embedding space to detect out of distribution examples. Others are kind of trying to use pseudo out of distribution examples, such as data from a really broad distribution that might cover your out of distribution examples. And then the last class of methods are most similar to ours that use unlabeled target distribution data, either by simply just training a classifier between the training data and the unlabeled target data, or trying to maximize ensemble diversity on unlabeled target data. Cool. So we start by comparing to the standard and the pseudo OOD methods on this aggregated CFAR out of distribution detection benchmark. And what we find here, and this is averaged over 5 different out of distribution examples, we find that compared to the best standard and the best pseudo OOD methods, we're able to actually pretty significantly outperform these prior methods across the board, both in terms of false positive rates and also in terms of kind of area under the curve. And across the 5 different out of distribution data sets, this data-driven confidence minimization method is consistently the best on all 5 of the data sets. So really what this means is that leveraging unlabeled target data really allows for substantial improvements in terms of OOD detection. And in full results, in our full results, we found kind of a large improvement on 9 out of 10 of the out of distribution data sets that we considered. This is just averaged over 5 of the out of distribution data sets for the CFAR'100 in distribution data set. We also looked at a more challenging near OOD detection benchmark. And here we're comparing to other transductive methods. And what we find here is that we can see a pretty consistent improvement over just training a binary classifier, the top row here. And on these 2 problems, we saw that we were either kind of getting pretty similar performance to ERD or outperforming ERD. And ERD is actually a method that trains an ensemble. It requires an ensemble of 3 different methods. And so it actually it requires 3 times the computational cost. And so it's nice that we are actually able to match or outperform that method with 3 times less computation cost. Great. And then the last results that I'll show is we ran a number of selective classification results. This is on a kind of a satellite image data set called Functional Map of the World. There's more results in the paper. I'll show results that are comparing to just a couple different things: the maximum softmax probability, binary classification, and fine tuning on the in distribution validation set. And compared to these 2 kind of fairly simple prior methods, we see that if the test data is in distribution, we're kind of fairly similar to fine tuning on the validation set. Whereas if we actually start to see out of distribution test data or a mix of in distribution and out of distribution test data, we're actually able to have a much greater performance. We see that kind of a 2 to 10% performance improvement on these test sets. Cool. So clearly the takeaway here is that this form of confidence minimization seems to be a promising approach for detecting if there's distribution shift and helping models know what they don't know. Now I'll quickly transition into talking a little bit about how we might improve predictions under some distribution shifts before going over the full takeaways. So in terms of improving predictions under some distribution shifts, I'll first note that all methods for trying to do this need to go beyond the standard in distribution or the standard independently and identically distributed assumptions. We need to introduce some new assumptions. Some methods for doing this assume that you have annotations on the domains in the data set, and then they try to learn representations that are invariant to the domain. This includes methods like domain adversarial neural networks and invariant risk minimization. Other approaches try to rebalance the data in some way, and the key idea is to upweight or upsample data points that are underrepresented. And there's a number of different methods for doing this, including things like group DRO, uniform class resampling, learning from failure, and so forth. And these prior methods can produce models that are robust to spurious correlations and domain shifts in some settings, but they may require domain annotations, and they don't address more extreme forms of spurious correlations or underspecification. And so we're going to try to tackle those challenges. And in this, I'd like to start with a really simple example where we have two different features, and our goal is just to perform binary classification between the positive training examples in blue and the negative training examples in red. This is a 2D example, but you could also imagine that these features could be other features in the data set, like the colors of cars or the speeds of cars or something like that. And even in this really simple data set, if the gray data points are test examples, we actually see that the data set is somewhat underspecified. It's kind of inherently unclear what the correct decision boundary is, and all of them achieve a rather low training loss. And they can't all be correct because they're going to be making different predictions on the test examples. So which feature should the model pay attention to? And I should emphasize here is that really this problem is underspecified only because there's covariate shift. If there wasn't any covariate shift and we kept on getting more training data points from the training distribution or more test data points from the training distribution, we wouldn't have any problems with classifying this data set. So in trying to tackle this problem, one thing we could do is try to regularize towards the correct function, but this would require domain knowledge or requires, and additionally requires some way to convert that domain knowledge into a regularizer, which can be rather challenging. Alternatively, we could try to learn a Bayesian posterior over parameters and kind of basically learn the full range of possible solutions. But these methods generally don't scale well to deep neural networks. Now, to approximate the Bayesian posterior, you could also train an ensemble of neural networks to try to cover the space of possible functions such that you could then narrow it down to one of them. However, if you train an ensemble with different random seeds, you'll actually get very similar functions for classifying these data points. And so they show very little disagreement even on this really toy data set. And this can be worse if you have kind of forms of simplicity bias or something like that. And so what we're going to try to do is we're going to try to sort of train the ensemble, but try to actively diversify the ensemble using unlabeled data from the test distribution. And so what this will look like is we're going to train multiple functions. This could be a full ensemble, or it could simply be a neural network with multiple heads. We're not going to just naively train these. We're going to train them such that they minimize training error and such that they have maximal disagreement on data points from the target distribution. And to maximize this disagreement, we don't actually need any labels from this target data. And so specifically, we'll train a neural network that looks like this. We'll try to push apart those heads in our hypothesis space and ultimately try to get something that, for example, like one function that pays attention to one feature and another function that pays attention to the other feature. Then once we learn these diverse functions, all we need to do is figure out which well, first this can tell us if our data set is underspecified in the first place, and then we can figure out which one of these functions or which one of these features the model should be using. And so in the second stage, we will try to disambiguate the correct function. And there's a few possible options for selecting them ahead. One would be to randomly label some of our test data points and select the most accurate head. You can actually do this a little bit more efficiently and actually explicitly query for the data points that are most disagreed upon. Get the label for those data points and then select the most accurate head. This is going to be more efficient. Alternatively, if you have interpretability methods that can tell you what features the model is using, you could use those methods to inspect the learn functions and pick the correct feature. Cool. So how does this work? We can start with a very toy example and actually look at the two functions that it learns, and we see that it learns one function that pays attention to one feature and another function that pays attention to the other feature. So this is pretty cool. And if you actually give it more than two functions, it'll cover the space more completely. I think that in terms of the DivDis method, I think that one of the big takeaways, at least for me, is that when you have a labeled data set, that may not fully specify the function that you're trying to learn, especially when you have distribution shift. And learning diverse functions is one way that can tell you that there might be underspecification in the data, and also one way for trying to consider those different solutions. Of course, we can also consider other ways for help specifying a function that might kind of augment the training data set, such as data augmentation, but other ways of actually trying to help figure out what the true function should be and make sure the model actually learns that true function. Yeah, and so kind of overall, I talked both about the benchmarking process with wilds and wilds time, as well as methods for detecting distribution shift with confidence minimization, and methods for learning multiple diverse solutions to handle distribution shift. I'd like to really highlight the students and postdocs who led this work: Pangwei, Shiori, Huashu, Caroline, Fahim, and Yunho. And if you're working on distribution shift, I'd encourage you to check out some of the benchmarks.